Okay, so thanks everyone for joining us today. And here's the agenda for today, and we'll have the notebook tutorial presentations for the first hours, and then go into the potential breakout rooms. So please think about what topics you want to work on today. And there are a couple of suggestions available in the table. If you are interested in working on any of these or something else, we can make breakout rooms for you. And then the main room will be for general Q&A session as usual. And then when the presentations are over, we'll have come back to this slide and then decide what breakout rooms we want to make. Okay, and we have two announcements today. For those of you who missed the announcement about the revised timeline for the Rubin Early Science program last week, and then about the citable DOI information as well. Please check the this post, and then for the full information, go to the RTN 011 for the details. And then for the future virtual seminars, next week we're gonna have a normal Stack Club, and then 2 weeks from now there will be a special delegate assembly. We'll have a special guest, Jen Kotler, a Space Telescope, who will present on the importance of accessibility and authoring guidelines for the notebooks. And then we have the hackathons after the talk. Okay, and then before jumping into the first notebook that will be presented by Christina, let me introduce myself briefly, as this is my first presentation at Delegate Assembly. So my name is Yumi Choi. I did my PhD at University of Washington. And my research background is resolved stellar populations in nearby galaxies. And I study stellar structures, kinematics of the Magellanic Cloud, in star formation histories of the nearby dwarf galaxies. And also, I'm interested in dusty ISM, particularly the interactions with the massive stars. And after my PhD, I did 2 postdocs at Stewart and NOAO and the Space Telescope. And before I joined NOAA Lab last May, I was at assistant researcher at UC Berkeley. And in the NOAA Lab, I worked in the Rubin CST and also NOAA Lab CSDC data lab team. Okay, I think that's it. And Krishna, the floor is yours.
Yeah, thank you. Maybe I will, so I'll reshare. Hold on, let me get back to that part. Okay, can you all see my screen now? Okay, so today we're gonna go through 2 new DP0.3 notebooks that target the learning about solar system bodies through their phase curves and how you can use DP0.3 simulated data to sort of learn how to do this with real LSST data once it comes in. So we're going to go through notebooks 4A and 4B in part, and both of those have a bit of background information in the introduction. So I'm just going to go through those in a slide instead of in the notebook, because diagrams are more useful, I think, in this case. So both of these notebooks we're going to go through are about measuring phase curves in DP0.3. And so this diagram is showing what exactly that means. So there's the sun orbiting around the Earth, and then you have solar system bodies like asteroids orbiting around the sun, either outside or outside of the Earth's orbit. And so the phase angle is this angle alpha, which is it's kind of analogous to moon phases, where depending on the angle between the Earth and the sun and the asteroid, only a fraction of the asteroid will be illuminated at any given time. And so the fraction of illumination will change over time. And so you can measure the difference in apparent magnitudes that reflect sort of the fraction of the asteroid that's being illuminated at any given time. And this helps us, so if you can measure how this changes with time, you can try to use that to reconstruct the intrinsic properties of asteroids, like the surface properties, the albedo, and what type of solar system body it is. So that's sort of the overall goal of measuring phase curves, is to try to reconstruct those measurements. So in DP0.3, there are measurements of the apparent magnitude, and so we can use those to see how the apparent magnitude changes with over time due to differences in the illumination, and then also due to the distance from the Earth and the Sun. So alpha is the phase angle. That's this angle here in the diagram. Two other things that we're going to talk about are the topocentric distance, which is the distance from between the Earth and the asteroid at any given time, and then the heliocentric distance, which is the distance from the Sun to the asteroid at any given time. So we're going to model all of these changes in what's called a phase curve, which quantifies the magnitude differences as a function of angle. And this helps us to reconstruct the intrinsic properties. So just a quick overview of what these phase curves look like when you actually calculate them and measure them and try to model them. So what we end up plotting here is the reduced magnitude. So that's the magnitude as a function of the phase angle. So the angle between the Earth and the asteroid and the Sun. And you plot those as a function of the phase angle. So you can see how the magnitude, this quantifies how the magnitude changes as a function of this angle. And so here's an example phase curve from a very well-studied asteroid. And so you can see kind of what this looks like, that at low phase angle, close to zero, the reduced magnitude is much brighter because most of the asteroid is illuminated. And then as you go to farther and farther phase angles where the a smaller fraction of the asteroid is illuminated, you get lower magnitude. So you can model this behavior to try to reconstruct the intrinsic properties. And so there's a number of different ways to do this. There's different assumptions you can make about the model shape. And so some different solar system bodies will warrant different assumptions about the model shape, but we're going to talk about a few of them that are used in the DP0.3 data set. And so these few sets that we're going to talk about are we're just going to explain those here. So the sort of most basic model that we discuss is the HG model, where you have two parameters describing the behavior. So there's the reduced magnitude, the absolute magnitude H, which is the reduced magnitude at phase angle 0, and then G, which is a separate parameter that sort of contains all the intrinsic properties you could back out later. So this is the form of the curve that's shown in this plot. There's two other forms that are a little bit more complicated in the form of the mathematical model, that are the HG1-2 and HG1-G2. So you may see those throughout the notebooks. And the introduction in the notebooks explain what those are and what the formats are. Okay, so for today's notebook, we're going to talk about, for today's delegate assembly, we're going to look at two of these notebooks, DP0.3 04A and 04B. So maybe now, if you want to follow along, we're going to open up and start with 04A, which is the introduction to phase curves. So here are the instructions for how to download those. I assume most people have already done this, but if somebody needs a minute to sort of pull these down and open them up, we can wait a couple minutes.
No one should have to do that. It's
okay,
all
great.
automatically in your notebook/tutorial notebooks directory. Yeah.
Okay, great. All right, so then we'll just go right to the notebook. So so here is the DP0. The 04A notebook. So this is the introduction to the phase curve one. So I just went through this introduction in the last two slides. So we're going to start over here with the package imports. So we import a bunch of useful packages that we need for the various plotting and other things. And we import some of the LSST RSP packages and open up a TAP service. So Here we're just setting up some criteria for the plotting. We have a bunch of functions that get used periodically. So there is a function for calculating the semi-major axis of the asteroid. So I showed you this model that is the model we assume when we model the phase curves. These are some of the coefficients that go into that model. So we load them up here. Here is one of the model forms that I was showing in the last plot or in the last slide. So this is the HG1, G2. So we just define the form of the model so that we can plot it later against the DP0.3 data. Here's the simple one that I showed you in the plot earlier. Sorry, this isn't the simple one. Sorry, this is the HG1-2 model. This is one of the models that we also get assumed, and I think this is a simple. So sorry, I should just overview this. So I showed you the simple format of the model in the slide. This one is sort of a more complicated form with more parameters, but it allows you to do a better job at modeling the behavior when you have limited data sets. So if the phase angle is not very long, so for example, if the object is very far away, then it takes a really long time to cover a range of phase angles in your data. And so when you have limited data, it can be easier to use one of these more complicated models to describe the behavior. And then this one, the HG1-2 model, is the one that is actually used by the DP0.3 data set. So DP0.3 contains already some automated measurements of the phase angle parameters. And so this is the model that's assumed when making those measurements in the DP0.3. All right, so let's move on to section 2. So the first thing we're going to do is plot the phase curves of a few asteroids in the DP0.3 data set. So first we're going to start the TAP service for DP0.3. And that's cell 8. And then we're going to query the SS object table and the MPC orb catalogs to obtain sort of the intrinsic properties of the objects that are in the DP0.3 data set. So to do this, we're just going to start by picking a select number that we think are going to have good measurements. So we choose some that have a number of observations greater than 100. So that means that they're going to be well sampled by the LSST simulated data. And then we pick some that are at a perihelion distance or Q of less than 50 AU. And so that means that these things are relatively close to Earth, and so potentially brighter, and are going to have higher quality data in the LSST data set. So we set these thresholds here in cell 9, and then we run this query. So we're going to query for those parameters, objects that have lots of observations and are closer than 50 AU from the sun. So we get a number of objects. We get 2.5 million objects. So here's the table of those parameters. So we've retrieved a number of the orbital parameters and a number of the phase curve, the parameters for the automated phase curve modeling that is contained in the DP0.3 data set. So we have these stored in a table called unique object table. So unique objects so every object is going to be observed many times by the LSST survey, because these objects will move across the sky and will be measured in multiple generations of imaging. So, but the unique object table that we've queried here are specifications for individual objects that have been tracked across all of the data, but have been linked back to one single solar system body. So that's what unique object refers to here. Okay, so now we have this full data table of unique objects that are in the solar system that have been detected at some point with LSST DP0.3. So from this set, we're going to try to identify 3 different populations. Oh, there's a question in the chat. Oh, yeah. Okay, sorry. I ran this earlier because this query, so the query for the unique object table that we've defined here takes about 3.5 minutes. So maybe I'll pause here and ask if there are any questions that have come up while people's queries are still running. Oh no, everyone's getting errors.
Yeah.
Is this a limited size container issue, or is
No.
this
No,
something-
I think large.
Yeah, I was running with the large as well. We saw this error yesterday when a bunch of us tried to do really large queries all at the same time. Same error, same thing. So let me see, the way we can get around it is by just making the query smaller. So let me make a little, I'll post in the chat a little addition to the where we'll just get a smaller number of objects back.
Okay.
Hang on 1 second. Yeah, I'll test it and report back.
Okay,
So
so
I
maybe
think-
while Melissa's doing that, does anyone have any questions? Yeah, it's true. So Q less than 50 AU is nearly everything. We decided to retrieve a bunch of objects like that because then we could show the differences in the phase curves as you go between distant solar system bodies and nearby solar system bodies. So we did not test this out with a number of people running the query at the same time, so I'm sorry about that. Does anyone have any questions about the content so far besides the query crashing?
Could you go into a little more detail on the parameters? I mean, that you said they're good for sparse, but I was just wondering a little bit more why they're good for sparse. What's been added?
So this is reaching the limit of my understanding of solar system astronomy because I'm a galaxy astronomer, but my understanding is that, so here, I'll just scroll back up to the form of the forms here that are in the introduction. So my understanding is that the basic one is sort of the HG model, which has just 2 parameters. But if you start to include these sort of more complex models with G1 and G2 and some other sort of basis functions, this helps to accommodate. So what we found when we tried to figure out what this is, it's because it accommodates various observational effects like the photometric quality and incomplete phase angle sampling. So I think what that means is that if you only have like sparsely measured data points, you can sort of be less biased towards a small number of data points. And maybe it may be that, but I don't know, perhaps there might be a solar system astronomer on the call right now that would have a better explanation. How about Jamie Robinson?
Hi everyone. Yeah, no, I think you're quite right there, Christina, but I can maybe explain in a tiny bit more detail if that's
Sure.
okay.
Yeah.
Because yeah, basically the HG model is sort of the simplest model, and it's like a 2-parameter fit. One is H, which is absolute magnitude, it's the y-intercept, and then G controls the form of the curve. And then whenever you go to H, G1, G2, that's actually a 3-parameter model where you have H again, but now you have 2 different parameters to control the form of that curve. And the value of G1 and the value of G2, they sort of determine the strength of the different basis functions. So there's like the basis functions describing that curve, and then I can't remember which way around it is, but one of the functions is more weighted to describing the low phase angle, like the large nonlinear section. And then one of the basis functions is more focused on the larger phase angles, which is a bit more linear in shape. And then what's actually happening when you go from H, G1, G2, the 3-parameter model, to the H, G1 to 2-parameter model is now, I think if you scroll down ever so slightly on your shared screen, what you're actually doing is you are the HG12 model is like a constrained version of the 3-parameter model where the values, the value of G1 and G2 they sort of follow a set constraint curve basically. So it's based on the same function at the end of the day, but you're constraining the values of G1 and G2 based on the fit.
So a little more piecewise.
Yeah, I think so.
Thank you.
Cool. And then Christina, sorry, if that question is answered, I have a very quick question just about the data in DP0.3, if that's okay.
Sure. Yeah. Okay.
So I was just wondering, because I think I've played with the precursor to this before, so I'm assuming that DP0.3 doesn't contain like rotational brightness variation or other like shape-driven brightness effects.
I think that's right. But if somebody else wants to comment further on that, I think that my answer is yes, you're right, that it doesn't include those.
That's correct. Yeah,
Yeah.
there was no, everything is perfect spheres in there.
Yeah. Excellent. No, that's great because, like, yeah, this is super valuable for seeing the sort of phase angle ranges that we're going to get. So that's really great. But yeah, I think whenever I've worked with real data for phase curves, the enhanced scatter because of brightness variations becomes a real pain. So I'm really curious to see how LSST deals with that in the live run.
Okay. I saw some Slack chatter, or sorry, not Slack chatter, the chat in the chat box. Was there a resolution to the search query situation, or?
Yeah, I just posted something you can copy paste. You can change the where statement and only return 24,000 objects instead of all of them, which makes the query work, but it will make one of the plots fail later on because
Okay.
like an object of interest is now no longer in the big sample. But so that's the workaround.
Okay. Why don't so since I already ran my notebook, should I just keep going with the?
Yeah.
Okay, and then when we get to the point where people get different answers than me, we can compare the object that I show. We picked out a few good objects to show the phase curves. So
Yeah, we'll
give
just
you
look to you
variation.
for those
Okay.
plots. Yeah.
All right, sounds good. Okay, so I'll keep going. So we're going back down. So we've retrieved the unique object table. So now within the unique object table, we're going to try to identify subpopulations of asteroids according to sort of their distance from the sun. So we've split things up into main belt asteroids, which are the closer population, less than 3.25 AU. We have Jupiter Trojans at a more intermediate distance, and then trans-Newtonian objects that are way out beyond 30 AU. And so here to sort of help with our reconstruction of the phase curves, we're also picking objects that specifically have 2,000 or more observations, individual observations of those objects in DP0.3. Okay, so here we're selecting these. So we have the, we're sub-selecting the unique object table to identify these three populations, and in particular, the ones that have 2,000 or more individual observations. So we get a couple hundred in the asteroids and Jupiter Trojans, and then we find 38 TNOs that are with lots of observations, more than 2,000. Okay, so let's see what those things look like. We're just going to plot histograms of each population. So this is just showing the number of objects we retrieved as a function of the semi-major axis, just so you can visualize where they fall in the solar system. So you can see that the main belt asteroids are close in, we have Jupiter Trojans in the middle, and then TNOs way out in the far solar system. Okay, so now that we've identified individual objects from unique objects in the solar system from the SS object table, we're going to match those to all of their individual observations that have happened over time during the 10-year LSST DP0.3 data set. So we have to take those SS object IDs, which identify the unique objects, and we're going to match them to all of their individual observations from the SS source table and the DIA source table. So if you remember, the DIA source table is identifying from difference imaging, identifying changes that sources that are identified as changes from one image to the other. And then the SS source is individual observations of solar system bodies. So we match those. We're going to join those. We're going to search on the SS object ID, and then combine all of the individual observations for each unique source in something called the individual object table. So here it's indiv obs. So we perform that search to collect all of the observations of unique objects in individual images. And so we get this table here. There's about, is that 1 million? There's 1 million individual observations of unique objects in the 10-year data set. And so then in cell 14, we just sample those down to be the ones where we only got 2,000 observations or more of individual unique sources. Okay, so now that we have observations and over time for all of our unique objects in the solar system that we've pulled out, we're going to plot their phase curves and see what they look like. So first, we're going to start by plotting the phase curve of one of the main belt asteroid objects. So in order to do that, we have to first convert the apparent magnitude into what they call the reduced magnitude. So this is h as a function of phase angle. And so the h is the reduced magnitude. You convert apparent magnitude into h as a function of alpha by using the distance, the heliocentric and topocentric distances, which I showed in the diagram in the beginning. So this allows us to plot their reduced magnitude h. So we're going to make this conversion to get reduced magnitude. And then in cell 16, we're going to plot the phase curve for the main belt asteroid. So this is what the plot looks like here. So on the y-axis is the reduced magnitude. So we converted the apparent magnitude to the reduced magnitude using the heliocentric and topocentric distance. And then we plotted the phase angle, which is showing what fraction of the object is illuminated. And so this is what you see if you plot the phase curve for the object in 4 different filters. And so the reason for these being different is that the sun has a specific spectrum and the object has a reflectivity, and so they're not the same brightness in every filter, the asteroids are. So here you can see they're brighter in this particular asteroid is brighter in the Z and I bands, and it's faintest in the G band. So the data points here are what is contained in the DP0.3 data set. And then, there's a chat question. Okay. So yeah, so flat H is the absolute magnitude, which is when it's the reduced magnitude when the phase angle alpha is 0. So I guess I should have clarified that. But what we're plotting on the y-axis is actually not h, it's actually h of alpha. So when we fit the model to the data, what we're trying to retrieve out is h at alpha of 0. So the absolute magnitude when the object is fully illuminated. But again, I'm not a solar system astronomer, so if someone wants to add to that explanation, please, we're happy to hear it. Sorry, does that clear up the question in the chat?
I think the comment in the chat might actually be referring to the formula right up under 2.5 that expresses h as a function of alpha. I think maybe that's the one that should be v as a function of alpha.
Oh, does it matter what? But as long as you have magnitude in one filter, shouldn't the h also be the magnitude in the same filter?
So I think it's because here it's using h to express a variable as a function of alpha, but h is always a constant. It's always evaluated at a phase of 0. So I'm guessing.
Oh, I see. Okay.
Yeah, so I think that's what the comment is referring to.
Okay. Well, we can fix that in the notebook. Sorry about that. Okay. All right. So anyway, just to go back to this plot. So there's oh yeah. So yeah, no worries. Okay. So the curve that you see there, what we've plotted on top here is in the DP0.3 data set, we DP0.3 contains already automated fits to the phase curves for solar system bodies that have been uniquely identified. And so you can just pull out the H and the G12 parameters from the MCB orb table. So that's what we've done here. We're plotting the phase curve that the DP0.3 dataset has automatically generated. So you can, of course, go and model these yourself with any kind of model that you see fit. And so Yumi's going to talk about that in the next in the next notebook. But this gives you an example of how the DP0.3 data set is sort of containing information about the solar system bodies. So you can retrieve phase curve parameters that are automatically generated. And so that's what we're plotting here. Okay, so now we're going to, this is a main belt asteroid. So now we're going to compare the phase curves from a main belt asteroid in DP0.3 to some of the other solar system populations that are in there. So here we are just redoing this plot with the other two subpopulations that we pulled out of our search queries. And so here are the three plots that show the phase curves for three example solar system bodies. So there's the main belt asteroid from the first plot. Next to it in the middle, we're showing the Jupiter Trojans, which are at the intermediate distance from the sun. So you can see that their phase curves become more uncertain. The objects are fainter. Their orbits are longer. And so you probe a narrower range of phase angles for any given observation. So in this particular object, we only observed 10 degrees of phase change since the observations, because they're farther away from the sun, the orbit takes much longer. So in the 10-year lifetime of the survey, you probe a smaller range of its orbital span on the sky. And so the same thing is true for the TNOs, which are the farthest, and you only really probe a very small range of phase angles for TNO objects. And so the modeling for those objects is much more difficult. Ryan.
Christina, yeah, I just had a quick question about the, I guess the tables here. Like, are there going to be tables that have upper limits on, like the observations? Like, I think that would be equivalent of like the force source on DA object, where I think the SS object table, it doesn't seem like it has limits on observations. Is there going to be like an equivalent one for solar system objects?
I don't know the answer to that question, but maybe somebody on the call can answer that question.
I kind of missed the question a bit. What kind of limit?
Oh, yeah, I'm just thinking of like for DIA objects, those are only ones that have a signal to noise greater than 5. But then there's like a force source on DIA object table that does a force photometry that shows limits if it's not detected, right? So is there a similar thing for solar system objects? Like if you wanted to plot upper limits on the detections here for, say, the G-band photometry, where it's not detected?
Is there a force source on solar system objects table? I got to check the DPDD. I'm not sure. I'll check it. I'll see what the DPDD.
Okay, well, I guess that would be really difficult too if they're moving, right? So
No, you know where it is, so you could. Well, I guess it depends on the astrometry. So maybe wouldn't be good enough. You wouldn't have precise enough estimates of location at a certain time to do it. I'll check DPDD. I don't know.
Well,
Okay,
the astrometry shouldn't, if it's visible at all, the astrometry is just, it's the coordinates. So I don't think that you would have a problem with the astrometry itself.
Yeah, this is to make a measurement where there is no detection. So you need the coordinates, then you do a PSF fit to anything that's there, even if it's really low signal to noise ratio. And we do that for static sky objects, because that's like we know the coordinates a little better.
Yeah, I think it would depend on how many other observations there already are, how well the orbit itself is known, all the 6 orbital elements, in order to calculate the orbit more precisely. So if the orbit is not known really well yet, then the force photometry could be erroneous if it's picking up some other background noise. If the orbit is already known really well, then yes, it could work, I would think.
Yeah, I think it is not in the DPDD. There is no force source on solar system objects, and it's probably because you can't do it for all of them. So if you're only going to do it for the ones that have a good enough orbit fit and have good enough predicted astrometry, that's a user-generated data product. Yeah.
I see. So that means like the only photometry or measurements that are going to be made are the ones that are greater than signal to noise of 5. Is that right? So if there's something between like 3, that's not going to be in the catalog, like that needs to be done on your own.
I think that's correct. So it's detected sources and difference images only, and then those get linked together into the SS objects. I think there is potentially an exception there written in that says like, we will keep in the catalogs signal to noise ratio less than 3 detections in certain areas. And I believe like solar system keyholes are one of those areas, but this is very not determined yet.
Okay, thanks.
And Leanne's gonna chime in here.
Yeah, hi Melissa, thanks for that. Yes, that's correct. We do have a provision in the DPDD to trigger on objects that fall below the 5 sigma threshold. These are for very specifically defined science cases. It won't be for just anything. And as Melissa says, we haven't done that full study yet as to what those will be. There'll be a limited number and they'll be driven by a certain type of science. So this is something I think the science team has to pick up in the next year to write that down, to clearly quantify what that will look like and what the science drivers are.
Sorry, I was muted. Yumi, go ahead.
Yeah, so so this particular DP0.3 catalogs are not reporting the measurement from the images, right? So there's no simulated images, it's just the simulated catalogs, right? So maybe there's some difference between this DP0.3 and the real LSST catalogs.
Okay, I would like to share one thing that Melissa put in the chat, which is that actually for the very distant solar system bodies, they always look mostly illuminated from Earth because of their distance. So so the phase angle is actually due to that. And so okay, so shall I keep going? I think we have maybe 5 more minutes and then we can switch to the other notebook. Okay, so one of the other, sorry, that's my dog. All right, so now we can explore the uncertainty in the phase curve modeling for each of the filters. So I mentioned earlier that the galaxy, or sorry, not the galaxies, the asteroids are they are brighter in different filters due to the spectrum of the sun and also the reflectivity of the surface, and so they're not always the same brightness in every filter. And so we can see how the phase curve uncertainty in the modeling can change as a function of filter. So we're using again the unique object table and the individual object table that we have matched with all of the LSST observations, and we're going to choose some of the main belt asteroids in a number of filters to see how their fit uncertainties change. So we're selecting these things, and then we're going to grab the modeling, the best fit model plus the best fit model's uncertainties so that we can compare them. So here I'm showing one of the unique object from the main belt asteroid sample. And here you're seeing the G and the Z filters and the phase curves measured from the LSST data, along with the best fit model, which is the dashed line, and then also the shaded region is showing the uncertainties on those models that are also contained in the DP0.3 data set. So you can see that for sources that have higher uncertainties in their measurements, you get a larger range in the best fit uncertainties also. So these are parameters that are contained in the the DP0.3 data set that are automatically generated. Okay, so there's a number of other other data products that are contained. I'm going to skip over the rest of this stuff so that Yumi has a chance to show the second notebook. But just to point out that there are, if you go through these notebooks yourself, there's some other explorations later in this notebook that helps you sort of understand the population of objects and what the distribution of measurements from those objects looks like from the DP0.3 data set. Yumi, do you still need me to share the screen for you, or?
Yeah, my notebook server is not working. Yeah.
So I'll just bring this up then. And I'm just going to start it running so that because there's another query in there that takes a long time. So, all right, I'll mute, and then Yumi, direct me with the navigation on the screen.
Okay, thank you, Christina. Sorry, this morning we had some problems with the notebook servers. So it fixed for most of people, but still not working for me. So, Christina, thank you for sharing your screen for me. So this notebook B is particularly targeting more advanced users who are interested in delving into the phase curve fitting more in detail. So in this notebook, we're gonna explicitly investigate the derivation of phase curves particularly for the main belt asteroids, where we for which we have a good phase curve fittings in general. So many of the basic concepts are introduced by Christina and covered most part, but can you scroll down to all the different models? Yeah. So the reasoning behind why we focus on these three particular model is that the simplest HG model was providing the parameters for the simulation of the Rubin solar system object. So H and G values used to simulate the solar system object in the DP0.3. So those truth values are stored in the MPC org tables as MPCH and then MPCG. So those are the two parameters that were used to simulate the solar system object. And then and in the SS object table, the LSST will measure the HG1-2 model parameters and store them in the SS object table, which is the simplified two-parameter version of the HG1, G2 three-parameter models, which are more sophisticated models. But the HG1-2 model is effective enough for deriving the reliable like absolute magnitude and then slope parameters for poorly like sampled phase angle data sets. So this is the reason behind why we explore these particular three functional forms for the phase curve notebooks. Can you go down? Yeah, so in the first part, we're just importing the packages and libraries used for this notebook, and then we define functions and parameters. So the basic setup for plotting defaults, and then the filter or the colors and symbols for the LSST filters used, And then here are the coefficients for the fitting functions, and then there is a function define the HG model, and then the HG1, G2 model, and the function for the HG1, 2 model. And then there's a little function that computes the weighted error weighted deviation for a given model for used in the fitting process. And then the next function is define the fitting phase curve for a given data set to a designated model. And then the next one is when the data is given, then it will fit the data to the all three different phase curve functions. Okay, so these are the functions defined, and then the next cell. So here we now just query the data we are gonna use. So basically the same queries that Christina ran, but this one is particularly for the main belt asteroid, and we're gonna focus on the main belt asteroid that has number of observation greater than 2,000. And if you run this cell, then the unique main belt asteroid should be returned, and then the length of the table is 296. So I'll pause here, and if people have any problems with the executing this cell, because it should be short, right? It doesn't take that long. Yeah. So this one, everyone got the result back. Or do we have the same problems? Okay, then maybe can just move forward. And then so for each about 300 unique main belt asteroid, we're gonna query the individual measurements from the DIA source and SS source catalogs. So for the phase curve calculation or fitting, we need the magnitude in each filter and the magnitude errors in each filter, and time of the observation and phase angle and topocentric distance and the heliocentric distance at for individual observation for each unique object. So this query will take like 3 minutes. Oh no, it's also 18 seconds. Okay. So does anybody has any issues with the query? Okay, if not, we can move on to the actual fitting part. So first we need to compute the reduced magnitude, which is the normalized apparent magnitude, as if the object is observed at the 1 AU from both the sun and earth as a function of phase angle. So we calculate the reduced magnitude first, and then for individual unique object are fitting their observed data with the 3 different phase curve models here in this cell. So this cell takes usually like 3 minutes. Sometimes it took 6 minutes for my test. So this is why we limit our unique object number to the main belt asteroid that has observations more than 2,000. Otherwise, the fitting part will take really long. So we just try to optimize number of objects that we can do some investigations, but and with a good, not small number statistics, but still we can fit within a reasonable time. So while this run, is there any questions? Please ask.
I have a question on the data set itself. I think in one of the delegate sessions a couple of weeks ago, we were also working with the eccentricity and the perihelion distance and calculating the semi-major axis. And I think someone suggested it would be great if the semi-major axis was part of the actual data set instead of having to be calculated every time. Does anyone know if that might be moving forward or not?
I have to check the DPDD for that as well to see if semi-major access was a plan for the future that just didn't get implemented for DP 0.3. But I can say it is unlikely that any new columns will be added to DP 0.3 now, unless there's, for some reason, the whole thing gets re-released in the future. So for now in the foreseeable future, you'll have to make it for DP 0.3, but let me check the plans.
Okay. Thank you. Yeah, it's I mean, I'd understand not making any changes to DP03, but in future data releases.
Yeah, that's true. We are calculating A every time from the eccentricity and then Q.
Yeah, it does. The data products definitions document for the future MPC orb table does have A as a column.
Great, thank you.
Yeah.
Okay, then let's move on to the plotting part. So we now have all the fitted parameters for 3 different functions, and in the cell above here, we convert that the parameter dictionaries to individual columns in the pandas data frame. So it's easier for people to read each parameters. So that's one step there. And then for the plotting part, so we have about like 300 unique object. So you can pick any integer number between 0 and the length of the unique object number -1. So for as an example, we just pick 100 and then plot for this particular object. We overplot 3 different phase curve fitting results. So can you go down? Yeah, here in 4-band GRIZ. So for single object, we plot HG, HG12, and HG1, G2 model. You can see in the larger phase angle, like beyond 5 degree, all 3 fitting functions are basically the same, but there's some, the differences in the shorter, smaller phase angle regime, and that's actually resulting the slightly different absolute H magnitude, which is read off at the phase angle of 0, I think. Okay, so this is the difference, and then here we want to compare the manually derived phase curve parameters to those stored in the DP0.3 tables, particularly for the first, the HG12 model parameters, which are stored in the SS object table. So yeah, if you go down to the next cell, here we just compare the G slope parameter between what we measured in this notebook versus what stored in the SS object in old filter. And as we can see, they are on the 1-to-1 correlations as is expected. And then the reported errors are also very similar. And then the next plot, we compare the absolute magnitude, what we derived from this notebook versus what's stored in the SS object. So yes, they are I think identical because the DP0.3 pipeline also used the HG1-2 model to fit the phase curves. So this is really good and reasonable. And then next, we compare the derived HG model parameters with the input MPC or tables values. So to remind, HG model parameters were stored in the MPC orb table, and those values were used to simulate the DP0.3 Rubin observation. So in the plot, we compare the input, the output and input. Output is the what we derive from this notebook, and then input is the values stored in the MPC orb table. So in the slope parameter, for some reason, in all 4 bands, we see the bias in the output result. So this is unknown, not totally completely understood problem. So this might be one good the breakout room topic that if you are interested in to understand what's going on with this. So maybe this is showing a kind of intrinsic bias with the 10-year Rubin observations, or I don't know, but also we see some bias in the output and input for the absolute magnitude parameter as well, and this bias is larger than so the MPCH is in E band magnitude, and then we are GRI Z band. So there is a conversion between V and the GRI Z in the table linked in the text above the cell. But this output and input difference are larger than those filter conversion factors. So this is another bias. We don't understand completely what's going on with the simulation. So this might be a good thing to explore for the solar system object experts. Okay, I think we reached to the bottom of the notebook. So yeah, if you have any questions.
Thank you, guys. That's great. Round of applause. Yay.
Yeah. Right.
I got an error when I ran the step immediately below the paragraph 3.3, plot 3 different best fit phase curves. I can paste it in the chat. I don't know what happened. It says filts was not defined. And because that didn't work, the last step in 4.2 didn't work because the previous one didn't.
Maybe did you skip running the second cell under 1.2.1?
2.1.
That's the where we define fills.
Yes. Thank you.
Yep, no worries. Okay, any other questions?
Yeah, that fixed it. Thank you.
Yeah, great. Then I think we can go back to the slides.
Sorry, which slide did you want
the assembly, the breakup topic.
the break. Okay.
Yeah.
Mhm.
Yeah, so is there any topics you want to work on today? I think we're done with the presentation part. Oh, Bob, yes.
I'm trying to fit DP 0.2 stellar fluxes to a black body curve, and I'm woeful at it, and I was wondering if anybody could help me with that.
Yeah, I'm interested in. So maybe one breakout room for that and other topics. Oh, Jamie.
Hi, I don't know how much longer I can hang around for, but I have some thoughts about at least the bias in G, because I've recently been working on asteroid phase curves, but using data from the Atlas survey, and this actually seems to tie into stuff that I've been looking at before. So I was saying maybe I can like talk about that with some people for like 5 minutes before I have to go get my train.
That would be great because this is one of the mystery we didn't understand. Okay, anyone else? Right, if not, anyone who has the moderator privilege, can you make the breakout rooms?